Okay, first up, a trend line, line of best fit, line of least squares regression, those all mean the same thing. How can I write a line of best fit to describe a set of bivariate data? The line of best fit for a given scatter plot minimizes the squared differences, those are called residuals, from what the predicted values are based off of the trend line and the observed values from the data. Let's kind of break that sentence down. The difference between observed values and predicted values. There's a couple different things I want to mention in this chart. The observed data, these are the points in blue. The actual points that I've observed, I've collected data on, and plotted on my scatter plot. The predicted data are the corresponding kind of like X marks when I go either up or down from each of those different data points. Based off my equation, I can make a prediction about some value. How much Y I think there's going to be, how much response per variable there's going to be for a given amount of our explanatory variable. For an X value of 0, I expect to see a Y value of 0 using my trend line. The line of best fit minimizes the residuals or squared differences between those observed values and predicted values. I want there to be the least amount of distance between each data point and its predicted value on the line. I want to get my trend line to fit my data as best as possible by making these green distances as small as possible. Since you've got Schoology pulled up, could you open the Unit 3 S11 folder and find your way to this link, the least squares line GeoGebra applet. It's going to kind of let us see what I mean more about when it says line of least squares regression. All right. So GeoGebra on that link, least squares regression GeoGebra. GeoGebra on that link randomly plotted points of data here in red. And my goal is to try and manipulate my trend line to fit the data as well as possible. Right now, my trend line is y equals 0.22x plus 5.69. You probably have different numbers based off of how GeoGebra set up your scatter plot. My square area is 158.86. I'm going to show the squares. There should be a checkbox that says show squares. Let's look at this first square here on the far right. I have the observed value, the actual data point. I predicted this value based off of that given data. I see this is the data I've collected. I predicted this amount based off of the equation for the trend line. Does that make sense? For an x value of 14, I should have about 8 or 9. My actual data shows about 14. So there's a difference from what I've expected versus what I've seen in my actual data point. That difference is our error, our residual, the difference between the actual data and the predicted data based off of the equation of the trend. I'm going to take that difference and square it. And geometrically, that shows up like this little red square right here. That difference squared produces this area right here. Why do I have to square it? When I take this data point minus what's predicted, is that a positive number or a negative number? Yeah. This value minus this value, is that positive or negative? This value minus this value. Positive, right? Yeah. Okay. What about when I do this value minus this value? Negative. Don't I want all the differences to always be positive so that I can add them together and talk about what's the total square difference from the mean?
Yeah.
If I take a negative and I square it, it's going to be positive. That's why I have to do these differences squared. So that even though some are above the differences, or some of them are below, it's always going to be positive. Okay. Now, my trend line has a square area of 158.86. The best is 155, so I'm pretty close, but I can get even better by reducing the total squared area shown in red. So let's see if I can move these points around a little bit. Getting closer. 156. That's pretty good. Let's move use the other point. Wrong way. That's pretty close. I got 155.2. The best is 155.14 for mine. I'm trying to make as little area in red as possible, as little squared error as possible. Does that make sense? If I actually go ahead and click Show Best Line, yeah, I'm pretty close. I'm almost right on top of it now. Any other line is going to have more residual error. When I move off that line, I increase the squared error from what the best one should be. I made the area in red larger than it's supposed to be, and I'm trying to minimize it. I can hit refresh and get another one here. 286, it needs to be 170. One's a little bit harder. I'm off by about one there. But there we go. All right. So we've talked about residuals. Residual is the error in our prediction. A residual is the difference from what I've expected based off of my trend line. The residual is any difference in the observed data from the predicted value from the trend line. Better fitting trend lines have smaller residuals. I'm trying to make that squared error as small as possible. Okay, now it's very important how I define the residual. The residual is the actual value, the observed data, minus the predicted data. This difference right here. Subtraction is not the same thing backwards and forwards, so I have to do observed minus predicted, so that if I have a positive residual, it indicates that my observed data is more than I would have expected. My data point is above the trend line. Vice versa, a negative residual tells me that my actual data was below the line of best fit. A negative residual is where I had less than I expected. Let's look back at this scatter plot here. Would this point have a positive or negative residual? Positive, because the actual data is larger than what's predicted for its corresponding point on the trend line. Positive residual means that the observed is greater than the predicted. It's more than you would have thought. The actual data is more than I would have predicted based off of my trend. This point, vice versa, has what type of residual? Positive or negative? Negative, because it's less than I would have thought, right? When I do observed this value minus predicted this value, I'm taking a smaller number minus a larger number, which makes it negative. Observed minus predicted makes the signs make sense. So if it's a positive residual, you have more than you would have thought. Negative residual, less than you would have thought, less than you would have predicted. Observed minus predicted. Okay, we're going to be doing what's called residual plots. An example of a residual plot is what I have right here. Here is a scatter plot and trend line for the relationship between stopping distance in meters and speed in kilometers per hour. When you're traveling at this distance, how far do you travel after you press the brake before you come to a complete stop? That's going to increase the faster you're going, right? There's a positive relationship there. So all these residuals have been plotted. I'm taking all of these horizontal, vertical differences, and then plotting them over here on the right. So I can see this difference is plotted right here. This difference, this residual error, is plotted right there. If your residual is in the middle, what does that mean? If your residual is pretty close to zero, follows the trend, right? There's very little error in the prediction because the predicted value and observed value are very close together. If you have a larger residual, there's more error. You have more or less than you would have thought based off of your trend line equation. I'm trying to get all those residuals to be as close to zero as possible. Let's look at some residual plots. There's 3 residual plots. 2 of them I have some issues with. 1 of them is doing just fine. Let's look at this one on the right. I've got the residuals kind of following this form right there. As I traced over that with my hand, what form was that? Is it linear or nonlinear? Nonlinear. Would a trend line be a very good fit for that data if that's what the residual plot looks like? No. No, I'd probably use a nonlinear best fit example, a nonlinear regression model. How about this middle one? Look at the residuals as I go from small values on the left to larger values on the right. What's happening to the residual error as I increase from left to right?
It's increasing.
It's increasing, right? It's a really good fit for small x values, but not as good a fit for the larger x values, right? I can find a better linear model in that sense because there's not a common variance in the residuals. There's more variance here in the residual error than there is here. That one on the far left, that is probably an example of a residual plot or a true line of best fit because there's an equal variance from left to right in the residual plot. There's a similar spread in the values on the left in the residuals as there is on the right for the residuals. All right. Next up, here's a slide to tell us the formulas on how to write an equation for the line of best fit. Remember back to linear equations. I know it's maybe been since Algebra 1. Equations of lines. Y equals mx plus b. I don't remember the name of a line that's solved for y in the form y equals mx plus b. Slope intercept form. You bet. We're going to write equations of trend lines in what's called slope-intercept form. Y equals mx plus b. So to write an equation in slope-intercept form, obviously I need the slope and the y-intercept. Formulas for those are right here. To find the slope of a regression line, I take our value. This is the same correlation coefficient that we calculated in our last assessment, times the rate of change in y over x. Slope means change in y over change in x. But for these regression models, it's the standard deviation of y divided by the standard deviation of x. Slope. Slope m equals r times the rate of change in the variance. Standard deviation of y divided by standard deviation of x. Part 2 is going to help you figure out how to get the rest, how to get the y-intercept. It just so happens that every trend line must pass through what's called the centroid. The centroid is the coordinate.
Laney and Tommy Madden, please report to the secondary office. Laney and Tommy Madden, report to the secondary office.
It just so happens that the centroid is a point on every single trend line equation. the predicted value for x bar, the mean of all the x values, is y bar, the average of all the y values. This point is on every single trend line equation. So if I go to y equals mx plus b, and I know that x bar comma y bar, the average of x and average of y is a point on the line, I can substitute that in for x and y. I'll replace y with the y bar value. I'll replace x with the x bar value. I'm trying to find what the y-intercept is equal to. So how do I solve for b in this equation? What do I need to solve for b with? How do I do that? Okay, so if I want to get b by itself, what do I do to each side of my equation? Not divide, subtract. I need to get rid of adding m times x bar, so I subtract it. And that's the same formula that's on the board and on the screen. The y-intercept is the difference in y bar minus the slope m times x bar. If you know the slope of the line and a point on the line, I can write an equation of it. I can define the line in terms of a point on the line and its slope. So the y-intercept is y bar minus m times x bar. All right. I think the last thing we're going to do here is talk about how to interpret the line of best fit. We've got residual error. Residual is the difference between what we're actually seeing in the data versus what we're predicting from the trend line. We've got equations for trend lines. We know how to find the slope and y-intercept to write the equation. Now, how do I interpret in context what our trend line is telling us about our data? Let me make up an equation here. I'm going to make a table of values for a line. Let's make an x, y, t table for this equation. Y equals 2x minus 3. And I'm going to find the y value for a bunch of different x values. 0, 1, 2, 3. That should be good. So if x is 0, how do I find the value of y? And y equals 2x minus 3. Plug it in, obviously. Y is equal to 2 times our x value is 0, minus 3, that's negative 3. When x is 1, 2 times 1 is 2, minus 3 is negative 1. When x is 2, 2 times 2 is 4, minus 3 is positive 1. When x is 3, 2 times 3 is 6, minus 3 is 3. What is the slope of that line? What is the slope of this line? It's in slope-intercept form. You should be able to look at that and know what the slope is, right? It's 2. So what's happening in the table whenever x increases by 1? As x goes up by 1, what happens to y? Because that's the rate of change, right? Every time I move down the row 1, y increases by 2. So to interpret the slope, we're going to use this phrase. As x changes by 1, y changes by our slope m on average. There is some variability because not every point in the scatter plot is going to be on the equation of the trend line. But on average, as x changes by 1 in our scatter plot, in our data, we expect to see y changing by a value of m on average. You find that same interpretation up on the television screen. All right. You understand what slope is? Slope is the rate of change. How about the y-intercept? What does the y-intercept mean about a line?
Where the passes to the y.
Okay, so if the y-intercept is on the y-axis, what does the x value have to be?
0.
To guarantee that the point on the y-axis, you make x into 0. When x is 0, what's the y-intercept in y equals 2x minus 3? Just this last number, the b value. So y-intercept means that x has to be 0. So to interpret the y-intercept in an equation of a trend line, when x is equal to 0, when our explanatory variable is 0, we expect the value of our response variable y to be equal to b. It's the predicted value in y when x equals 0, as we understand our y-intercept. All right, last one, the coefficient of determination. This is called r squared. It's a new value for you. R squared is the same correlation coefficient, our R value from our last standard, times itself. R squared is R times R, right? R squared, the coefficient of determination, tells us how good our trend line is at describing the variation in our data. How good our trend line is at matching the data. R squared, as its interpretation, is the percent of variability in y that is explained by the variability in. What proportion of the variability in y is explained by the variability in? We're going to interpret slope, y-intercept, and calculate our r squared value to determine how good of a fit the line is for our data. The more r squared is closer to 100%, the better the fit. The closer r squared is to 0%, the less good the fit. One last thing here, interpolation and extrapolation. Be very wary of making predictions using extrapolation. Interpolation is making predictions within our set of data. Extrapolation is making predictions beyond our data. Typically, making a prediction beyond our given data, extrapolation, will be very dangerous. Because I don't know what's going to happen. Trends can change. Who knows what happens beyond the data I've collected? Let me give you an example of that. Interpolation is within the data. Here's the set of data to predict stopping distance based on speed. Give me a number within this data range between 0 and 40. Give me any number. 2. A little bit. Come on. Give me a different number. 30. Cool. I'm going to predict the stopping distance when I'm traveling 30 kilometers per hour. So I go up here and over about 15 or 16 meters. That's called interpolation because I am predicting within my known data range. What's a number that's beyond 40? 41. How about 75? What would the stopping distance be if you're traveling 75 kilometers per hour? Do I have data to predict that? Yeah. Does this go out to 75?
No.
No, that's extrapolation. I'm predicting beyond what I've collected data for. Who knows what happens out there? That's dangerous. Trends could change. I can make that prediction, but it might not be very accurate. All right, I think we're going to start calculating trendline equations and making predictions for a set of data next week. Otherwise, have a good weekend.
He did.